Hi friends, today we are going to see how to implement a multi-stage sampling rate converter. Basically, the design of a multi-stage sample rate converter is not that easy. It requires a laborious stage solution or iterative solution. So let us see how we can do it. Let us take a problem. The problem says that design a two-stage decimator with sampling rate to be reduced from 10 kilohertz to 500 hertz. Okay, and the passband edge, the requirement to avoid aliasing is given as this. The passband edge is given as 150 hertz, stopband edge is given as 180 hertz, passband ripples is 0.002 and stopband ripple is 0.001. Okay, so how to proceed? Let us say first I need to understand that what decimation rate should I use, because I don't know what is the value of D over here to reduce the sampling, right? So let us first find what is the decimation rate. Solution. Let us get to step 1 to find D. That is what is the decimation rate. So to find D, what I'm going to do? I'm going to divide, right? So to what I will divide? I have 10,000 hertz. Okay, was the input frequency, and I wanted to get 5,000 hertz as the output frequency. So what it will give me? It will give me 20. So I need to design. Okay, how should be my design for 20? It should look like I need to incorporate a filter to avoid aliasing, and the output of the filter will go to a decimator. The input sampling rate over here is 10,000 hertz, which is fx, and fy is 500 hertz. Therefore, the decimation factor requirement is 20. Okay, because we know that fy is equal to fx by d. Then d will be equal to fx by fy. That's why we got it to be 10,000 divided by 500. As simple. This is 20, which we have just calculated. This is step 1. Now, they have not mentioned that I have to use multi-stage, but number is quite large. If I wanted to design a filter for this huge decimation rate, okay, the filter complexity will also increase for the given passband, stopband requirement. Filter coefficient will really increase to a higher extent. Okay, you can do as a homework by the formula that I will give you, that how much value will be there of a filter if we use it only in a single in just this manner, that is in the single stage. But now we will design in multi-stage. Now what I'm going to do is I'm going to factorize my D as D1 in cross D2. Let's say 10 cross 2. Okay, so first stage I will make of 10, second stage I will make of 2. Okay, so how will my structure look like? The structure will be, I will have H1n, which will go as an input to a decimator of decimation factor 10. Then again I'll give an input to H2n, and then there will be a decimation factor of 2. Correct? So here the input will be x of n, and here we'll get y of m. Correct? Here this will be decimation fx by 10, and here the decimation will be fx by 10 into 2, which is nothing but 20. So we will acquire. Now we need to design the filter at stage 1 and filter at stage 2. Okay, so we want a filter to be designed at stage 1 and at stage 2. So let us see what are the formulas of which we need to use. The formula which we need to use is this 3. The passband on each stage is 0 to FPC. FPC over here is the passband edge frequency. Transition is passband edge frequency to Fi minus stopband edge frequency. And then stopband frequency will go from Fi to FSC and Fi to Fi minus 1 by 2. That is the stopband frequency. Using the relation above, okay, let's say at stage 1, okay, so I'm at stage 1 and my passband edge will be, so passband will be, okay, 0 less than equal to F less than equal to FPC. Okay, now we'll go to the given data of the problem and understand that what is given as FPC. So the given passband edge frequency is 150 Hertz in the problem. So I'll be using as 150 Hertz. Correct? Now where we are at stage number 1, where we have to go. We are designing the filter of stage number 1, right? So what will be stopband? Stopband will be stopband edge or stopband will be Fi minus FSC less than equal to F less than equal to Fi minus 1 by 2. Here I minus 1 is in the suffix part. Okay, it's not in the major part. Now for I equals to 1, I am at stage 1, you're at stage 1, I will be equal to 1. At I equal to 1, this becomes F1 minus FSC less than equal to F less than equal to F0 by 2. Correct? What is F0? F0 is nothing but Fx. Correct? That is the input. What is F0? F0 or Fx is 10,000 divided by 2 less than equal to F less than equal to, now what is F1? F1, that is the sampling frequency at stage 1 will be 1000. Okay, because 10,000 is divided by a factor of 10 will give me 1000, isn't it? Because F1 is Fx by D. Okay, so the D that we are using over here is 10, so it will be 1000 minus this will be FSC is 180, because in the problem the stopband edge is given at 180. Okay, so the factor comes around, calculation comes as 820 Hertz less than equal to F less than equal to, this becomes 5000 Hertz. Correct? So if I draw this characteristics, my stopband is from 820 Hertz to 5000 Hertz and my passband is from 0 to 150 Hertz. Okay, then what will be transition? Okay, transition will be wherever the passband edge is and wherever the start of the stopband is. So that is a transition. So 150, you can do 820 minus 150, that will be the transition band. Okay, so let us do it. If I draw the characteristics, in the characteristics over here with F as the x-axis, okay, and mod of h of f as the y-axis, we have the passband up to 150, and then after that it goes to 820, and onwards till 5000 it is 0. Everything is in terms of hertz. Okay, so the transition will be in from 820 to 150. Now this is stage 1 filter requirement. But what will be the order of the filter? To calculate the order of the filter, okay, we will go to a more technical requirements that is given in the problem. What they have still mentioned is my passband ripple should be 0.02. This is given as the overall passband ripples, and stopband should be 0.01. Correct? So now, if I want the overall passband of a cascade structure to be 0.02, okay, then if I am going to make a 0.02 passband ripple, let's say in stage 1 also and stage 2 also, what is going to happen is at each stage I am going to add more and more ripples. Okay, so passband becomes more repulsive because the total ripple that I have added in the cascade structure is 0.04, isn't it? Because when we see in the logarithmic scale, okay, this passband edge is going to get added. Okay, in linear scale you are going to see it as multiplied, but in actual practice it is going to get added. So my overall passband ripple, that is delta P, requirement is 0.002. So what I'll do is, at stage 1 I will divide this into two halves. So let's say 0.002 divided by 2 I'll do, okay, which is nothing but equal to 0.001. Okay, if you have it's like a binomial expression. What I mean to say is, let's say, just a technical information. If I have this passband ripples like this, okay, and these are my stopband ripples, right? So the maxima requirement is 1, let's say, and the minima requirement is delta P. Okay, so it is like 1 minus delta P the whole raised to n, and n will be the number of stages. So because delta P is less than 1, okay, I will expand it using binomial expansion, and then I am going to get this is equivalently n times of delta P. Okay, if you expand this, there will be more higher terms because delta P is smaller than 1, it is fractional, so the higher order terms will be very, very small and insignificant, so we can neglect it. So ultimately what really matters is this. So my delta P is going to be multiplied, or will be increased, or the ripples will be increased by a factor of n. Okay, and to avoid it, what I am going to do is, because I want the overall to be 0.02 in each stage, or if there are 3 stages, I will divide this by 3. If there are 4 stages, I will divide it by 4. Now there are 2 stages that we have considered, so I will divide it by 2. Okay, so delta P1 will be 0.01. Okay, then delta S. Now, if I say for delta S also to divide by 2, how does it really matters? Delta S is a very smaller quantity, okay, and by cascading in the stopband region, okay, the effect will not be much higher. Okay, once you reach in the stopband, it's stopband. Okay, I really don't care about. Okay, so when I'm saying delta S, I don't actually need to divide it by I will not actually divide this by any 2 or 3 or any stage number. I will keep it as it is. So when I'm saying delta P, I'm going to divide it. But when I'm saying delta S, because I'm not very much interested into stopband region, I will neglect that part, and I will keep delta S as it is in each stage. So delta S given in the problem is 0.0 0, 1. Okay. Now, with this practical consideration, okay, let's say step 2, find the odd of filter at stage 1. So, the order formula that I am going to use, you will be using is n equals to minus 10 log to the base 10 delta p1 delta s minus 13 divided by, okay, 14.6 delta f, okay, plus 1. Now you will say that it's a very tedious formula, can't help, you need to mug this up because this formula is been proved by Kaiser. Okay, there are basically 3 different types of formulas that we can use for FIR filter design if practical scenarios are given, that is the ripple factors is also given. Okay, so there are basically 3 various formulas available in the literature, but we will be using the Kaiser one. This is Kaiser formula. Now with this application, we know delta P1, we know delta S, okay, rest delta F we don't know, okay. So we need to calculate delta F. So delta F is nothing but transition, okay, transition frequency divided by, okay, input sampling frequency. Now input sampling frequency, if I say, this will be of that stage. This will not be always the normal input sampling frequency, but this will be at each stage, okay. So the transition width over here is 820 minus 150 Hertz divided by the input sampling frequency for this stage is 10,000 Hertz, isn't it? That will give me calculation as delta F to be equal to 0.067 Hertz, okay. This is my delta F. Fine. Now what I'll do is, I know delta F, I know all the parameters. Let us go to find the order. So the order n will be equal to, let's say at stage 1 is equal to n1, which is minus 10 log to the base 10, delta P1 is 0.01, okay, into delta S1, which is also 0.001, okay, divided by 14.6 delta F1, which is 0.067. Yeah, here I made a mistake. See, here we have 820 minus 150 divided by 10,000 Hertz, right? Hertz are going to get cancelled. So there will be no units for delta F, okay. So I will not have any units for delta F over here. Plus 1, okay. Have I missed something? Yes. Here it is minus 13 plus 1, okay. With that, the value of n comes as 49.04. So what you will do, you will approximate this to the next highest value, which is 50. You cannot design a filter with 49.04. What should I do for 04? What element should I put for 04? Isn't it? So to we normally raise it to one value, because that will actually affect the stop band characteristics and the cutoff frequency, and it will become more closer to the ideal situation. So this is at stage 1. So what we did at stage 1, let us summarize, because there are too many things we did. So summary of stage 1, if I write, what all things we did? So first we have jotted the characteristics. Okay, so we have jotted the characteristics. What were the characteristics? What were the characteristics we have jotted? We have jotted 0 less than equal to f less than equal to fpc, which are nothing but pass band characteristics. Then we jotted fi minus fsc less than equal to f less than equal to fi minus 1 by 2 as the stop band characteristics. With these two characteristics, I got the transition or the actual requirement, right? Then second, we have used the delta p delta s and found delta p1 comma delta s. So delta s no change, delta p we have to find delta p1. Delta p1 is nothing but delta p1 is equal to delta p upon the number of stages, let's say I. Okay, here the number of stages are 2, so I divided by 2. Third, we used delta p1. Okay, third point, we used delta p1 delta s, okay, and delta f, okay, which is nothing but transition upon transition band, all right, transition band upon input sampling of that stage. Using this, I have found the order. Order is minus 10 log to the base 10 delta p1 delta s minus 13 divided by 14.6 delta f plus 1. So these are the three basic steps that we did in stage 1. Let us go to stage 2. In stage 2, now we have come up to step number 2, I think so. Let's check. Yeah, step 2 we have written, but yeah, step 2 have written. Let's go to step 3. Okay, now we are at stage 2. Here my I will be equal to now 2. Correct. Now let us find again FPC and FSC. Sorry, yeah, FSC and FPC. Correct. So now for stage 2, pass band will be 0 less than equal to f less than equal to FPC. It is same as that of the previous one. And what is FPC? FPC is 150 Hertz, isn't it? Then what will be stop band? Now in stop band we have to take care. Now it will be F1, isn't it, minus FSC less than equal to f less than equal to F1, sorry, F2. Okay, yeah, F2 minus FSC less than equal to f less than equal to F1 by 2. What is F1? F1 is 1000 now, because we have already decimated by a factor of 10. So here F1, which is nothing but F0 by, let's say, 10, which is nothing but 1000. So my stop band comes to be F2 is 500, okay, minus FSC is 180 less than equal to f less than equal to F1 is 1000 by 2, which is which is 500. Okay, so that is what it is. Therefore my stop band will be now starting at, so my stop band will be 320 less than equal to f less than equal to 500 Hertz. If you draw the characteristics with f and mod of h of f, then this will be at now 150, because this will be at 150 and this will be at now starting at 320 and up to 500. Okay, then because we have delta P and delta S, we can go for the order of the filter. Now I will calculate delta P2, which is again equal to delta P upon 2 because stages are 2. So it is 0.001. Delta S1, sorry, delta S2 will be equal to same as that of delta S, right? What will be delta F now in this case? Delta F will be transition. Now what is transition? 320 minus 150 divided by what is the input sampling rate at this stage? It is 1000, isn't it? So that comes as 0.17. Okay, so you got delta P2, you got delta S2, you got delta F. So I'm ready to go with the order N2. N2 will be equal to minus 10 log to the base 10 delta S1, which is 0.001 into delta S2, which is nothing but again 0.001 minus 13 divided by 14.6 into delta F is 0.17. This is whole added with 1. This ratio is added with 1. So don't make mistake of writing this in numerator. That N2 comes around to be 19.9, which is approximately I will write as 20. So this is my N2. Okay. So this is how we normally design a two-stage structure. So now we know that if I draw the whole structure again, then I'm having an input with a filter h1 of n, and the order of this filter is n1, which is nothing but 50. Okay, then I'm going to go to the next stage with a downsampling rate of 10. Then we will go to having in stage 2, where I will have a filter with n2 to be equal to 20. Okay, and h2n, and then I will have a downsampling rate of 2, and that will give me y of m, and this will give me x of n. Now it is not mandatory that you do first the ratio by 10 and then by 2. It is not such. You can interchange the positions of 10 and 2. That's really easy. Okay, that's not a mandatory job that you have to first put the higher values and then go to the lower values. It's not so. You can interchange the position because it's a cascade configuration. It is ultimately giving you the same rate of decrease. Okay, so if I again summarize the stage 2, so what we did was first I calculated pass band, then we calculated stop band, isn't it? Then we went for delta P2 and delta S2 calculation, and we know that delta P2 is equal to delta P by 2 and delta S2 is equal to delta S. And third, using delta P, delta P2, delta S2 and delta F, I went to calculate the order. Okay, here you can also write delta F, which is nothing but transition upon input sampling. Please remember input sampling of that particular stage. Okay, at stage 1, if you can see here, this will be my F1. This will be my F1, which is nothing but 10,000 divided by 10, which is nothing but 1,000. And this will be my F0, which is nothing but 10,000. Okay, and this will be my F2, which is actually F1 upon 2, which is 1000 by 2, which is 500. Okay, so this is how we normally design a multi-stage sampling or multi-stage sampling rate converters. Thank you.